most of the things that we're talking about today are things that I learned the hard way as a graduate student. I had to beat my head against the wall on quite a few of these. Google was my best friend, and I'm sure it probably is yours. So a lot of these things are things that I kind of wish that I had learned or somebody had showed me before I got started. All the slides today are available here on this with this Google link. We're going to be getting the files from GitHub in just a little bit. So just so you know, we're going to talk for a little while. We're going to talk about version control, a little bit about compilation automation with Make. We're going to do a little discussion about code optimization, which includes debugging, as well as just hinting on or scratching the surface with profiling. And we're going to have an example time where we do a little bit of all three of those first things. And then we'll come back, we'll talk about scaling, we'll talk about some additional resources, and we'll get you on your way on this kind of bleak Friday afternoon. Our example is going to make use of Git, it's going to make use of Make, and then it's going to make use of GDB, and then also some other random little things. And again, experience is by far the best teacher that you're going to have. So my suggestion for you is that you go home, you enjoy your Friday night, and then later on, either over the weekend or early next week, try to replicate the examples that we have here, and then try to replicate it, these sorts of things using an analysis that you already have done. Right? It's always better to learn a new tool if you know the answer and aren't wading through all the difficulties with the actual analysis itself as well as the tool that you're using. So I put this slide up every time that I've taught the seminars. My suggested workflow for you when you're trying to get your code up and running all the way to being fully ready for production is to first build this in parts to get what I call a minimal working example. And so that's a small example case that requires all the functionality that you're going to need down the road, but yet it's still going to be at a small scale. So this is something that you can run quickly, run often. Later on when we talk about some of the things with the profiling and debugging, I hope it will be fairly obvious why you'd want something small and lightweight so that you can test out a lot of things very quickly. So after you get that up and running, then start to play with flags and options for optimization. At this point, I typically tell people start to submit your jobs even though you're only running in serial, because after that, it takes a little bit to actually make any real progress. It takes a lot of hard work. And so it's better to start getting results back at this point rather than wait for the whole flag before you actually get going. So the first thing that I suggest doing is always to rewrite your functions, to use optimized libraries. It will rewrite your functions first for your own optimization and then try to use the optimized libraries that are out there, MKL, Boost, and Petsy. And then at that point, that's when you need to start to think about parallelizing or accelerating on a GPU if you still need to do things. And again, my suggestion for everybody is to add as many comments as you can and to use descriptive variable names and function names. It's hard enough even coming back over the weekend, but if you put this down for a couple of weeks, you want to be able to pick up as quickly as possible. All right, so our first discussion is going to be about version control. So when I first started, my version control was having the name of the file change a little bit, either with the date or with a letter that kept getting incremented or something like that. But there's far better ways to keep track of multiple versions of your code. So there's different reasons why you'd want to do this. First of all, in the way that we typically talk about version control is for development purposes. Right? So if you have new functions that are coming on, if whatever project is in a semi-working state, but you're continually trying to either optimize things or modify things, that's a reason to have version control. Also, another thing, something that I experienced is especially in a graduate student lab, there's going to be multiple people probably working on the same code, and so version control is very useful for that. And then also, especially once you start doing production runs, you'll have different variations of your code, and so it's good to have some way to keep track of all these different variations. So some of the different variations might be for different purposes. Right? So if you have a version of the code that reads in this sort of input file that you get from, say, NIH, and if you're reading this version of the code, or use this version of the code if you're reading in files from, say, the NSF. Right? So you might have different versions of the code to be able to do different, or to use different inputs. You also might have different variations of your code if you're running on different hardware. So for example, a lot of people here run on probably your own personal computer. You have some workstation. Your code, especially a makefile or the different libraries, are going to look a little bit different on ACI. It might also look a little bit different if you're running on one of the NSF resources. So to be able to keep track of the different versions of the code that's ready to go for each of the different places that you actually run on is very helpful. So there's different types of version control. So the original version control, and this is pretty similar to how like I would just write the date at the end of the file, is what's called a local data model. So there's a single master repository. There's really one development point. So RCS, I had never heard of this one before, but it's actually one of the oldest types of version control out there. So if you look at the history of things, RCS and SCSS, as far as version control go, are two of the earliest systems that were out there. They're very rarely used now. The second type of version control is what's called client-server model. And so this is a little bit different. So here you have one master repository, right? So this is where you're saying, all right, everything that's there is what's up to date, is what's current, is what we're using for production. But then you have different development points. So for example, you might have your lab's primary repo, its master repo on git.psu.edu. But you might have your own repository on your own machine. And as soon as you're done, as soon as you've tested, when you say, all right, this is ready, then you push that up to that main master repository. So this is a pretty common way of doing things, even using the distributed model of version control, or at least the codes or the applications for the distributed model. But there are some versions of version control that only use this. So SVN is a fairly common subversion, is a fairly common type of version control that people use. It's probably the second most widely used type of version control. And then there's quite a few others, CVS and Vault as well. The last type of version control is called the distributed model. So with this, you don't actually have a master repository. And so, again, you have multiple development points, but within your own development point, you have a master branch, and I'll talk about branches here in a little bit, within that repository. So there is some additional going-ons that have to happen, some bookworking that has to happen, because you have to keep everything up to date. You don't have necessarily a master where you know that's where everybody pushes everything to its final stage. But there's a lot of benefits to using the distributed model of version control because you do have a lot more control, it's a lot more agile, and then if for some reason git.psu.edu goes down, you know that you're going to have your version on your computer that is the master, and you might save it in other places. So Git uses this distributed model. However, I kind of mentioned before, a lot of people use Git as if it's a client-server model, and that's okay. But I am going to suggest, and for example today, that you use Git. You have all the flexibility of the distributed model. You don't have to take advantage of that, but it is nice to have. The real reason why I'm going to suggest that we use Git is that it's very widely used, and it's very well documented. So both of these things are reasons that I think that Git's probably at least the best thing to use to get started. So there's 3 typical steps within the typical Git workflow. So your first step is to modify your files, right? You're either writing new things or you're fixing bugs, you're modifying the files, whatever you need to do. And then once you're done with that, the second step is to stage the files. And so in this, you're saying explicitly, this file is something that I want to save for later. I want to push this up to a branch. I want to save this for later use, however you want to call it. But staging the files is kind of an intermediate step between after you modify the files and then when you finally do commit the files. So that last step, that committing of your files, it does what it calls stores a snapshot. So it doesn't just change the deltas. You can look at the deltas, but it says, all right, at this time, at this date, when I committed these files, this is exactly what I had. And so that's very powerful because you can go back to an earlier snapshot, or you can create branches off of a snapshot. It gives you a lot of flexibility down the road. I talked about branches a little bit, and I hadn't really defined this term yet. So typically within Git, you have what's called a master branch. And it's kind of an ambiguous term. I like to say that that's where the current production version of the code lives. Right, so if you're getting ready to do your run, all you would really need to do in order to get started is pull that master branch. And so with that, you can initialize a new Git repository with Git init and then the period for here. But then you can have any other branches that you want, right? So you can have a branch for anything else. And so you can check out either an existing branch if there's already a branch that's there, or you can create a new branch with a checkout -b. And again, you can name it whatever. I highly suggest you make it a name that's something you'd be able to remember fairly easily, or be able to look at and know exactly what's going on in there. And so with your branches, that's where you would test new features, or you could have a branch for a specific cluster, a specific purpose, kind of like we've talked about before. But then there's two different things that you can do with branches. If you are testing new features, eventually what you're going to want to do is merge your branch, once you're happy with all of your code changes, all your new algorithms, back to the master branch. Or you can keep those branches separate. So if you're developing for non-standard purposes, either for a different cluster or different types of input files, you could keep these branches always separate. So there are some people that try to just bring everything back to the master every night. There's some people that like to have all their branches for all different things. And the reality is there's no right way to do it. It really depends more on your workflow. Okay, so I mentioned this before, but Git doesn't have a primary or a location where you know this is always where it is. This Git structure that exists with all the branches exists everywhere that you have a repository. And so it is up to you as the user to keep any other locations other than the location that you're actually working at as up to date as you desire. Right? So typically people will have their own Git repository on their local computer. They'll have it on the ACI clusters or whatever other cluster you're on. GitHub, you can sign up for an account there. If you, I think, pay $7 a month, you get a few, like 5 or 6 different repositories that are private. There's also a student version of this, and I apologize, I should have got the link for how to get that. And I think that gives you a couple of private repositories just for having a your pennstate.edu email address. And there are some other places that you might want to use. One thing to note is that when we talk about the origin, we're almost all, the origin is kind of a strange term. It seems like origin means master. It doesn't. So typically when we talk about another location, we say origin. So we'll come back to that later in the example. I just wanted to throw that out there now so that it didn't make anybody stumble later on. So within Git, there's a couple of different commands that we should know. So clone is to clone the entire branch structure, so the master and all the sub-branches. You could pull or push just individual branches or individual commits. Init, we mentioned before, is to initialize a new repo. When you're getting ready to stage your files, the command for that is to add. So you add either your new or updated modified files. And then commit is to commit the files. Checkout allows you to switch between branches. Diff allows you to see the differences between branches. And then merge puts a couple of branches together. So we're going to use quite a few of these in our example. So I don't expect you to know it all now or to remember it. I'll walk you through at that point. So one of the other nice things about using Git is that once you are comfortable with it, there's a lot of codes that are out there, open source codes that you can look at, that you can get started with, that you can incorporate into what you're doing yourself. GitHub is huge. There's a lot of different things there. I think all faculty and staff are able to get onto git.psu.edu, but students have to be added separately. I'm not exactly sure how that one works. But there's also, anybody can run their own Git repo if they like. And so there might be some that are specific for the codes that you're working on or the type of research that you do. So I would suggest asking around a little bit and then using Google. One of the reasons that I suggested that we use Git in the first place is that Git has excellent documentation. So this git-scm.com/doc has some of the best documentation for any of the version control software that's out there. And then this try.github.io allows you to, within your browser, bring up a little Java window and actually try and use Git. It walks you through all the different steps. It's a great way to get started. And then one of the other nice things about Git is that Now, outside of the get her done comedian, there aren't too many other things out there that are GIT, and so it's very easy to Google and find examples for just about anything that you like to do. Okay, so again, we're going to come back. We'll use Git quite a bit in our example, but now we're going to move on to compilation automation. So I'm assuming that all of you here either were at Seminar 2 in the fall or Seminar 3 a couple of weeks ago. So with that, you talked about how to optimize or how to compile your code. And you talked a little bit about some of the different optimization flags, ways to compile. The short story of all of that is that it can get very, very complicated very quickly, especially when you start to link to a bunch of libraries, or if you write some code that has some functionality that's shared between a lot of different codes, linking a lot of files together. And then also, because of the dependencies that might exist, a very specific order needs to be done, or everything needs to be done in a specific order in order for your executable to come out and work correctly. And so because of this, a lot of people use what's called a build automation system. So with that, you have all the compilation information in one place. It's very easy to look at, and if you know what you're looking at, be able to follow. So hopefully that's very easy to repeat, either on your own system if you're making some modifications, or on another system. And with that, because you have all the steps written out, it's very clear exactly what you need to change when you do port to a new system. And then one of the other nice things about build automation that isn't really important for smaller codes, but will become more and more important if you're getting to more complicated examples, is that these will only rebuild the required steps. Right? So if you change a single file, you don't have to remake every single object file that's out there in order to recompile everything. You're only going to have to change whatever depends on that file. And so the build automation systems have a way of knowing what those files are, and so it only rebuilds the portions of your code that need to be rebuilt, and won't do a full compilation every time. So there's a couple of different common tools that are out there. Make is the most commonly used tool. It's also the most basic. We're going to start with Make here today. Our example is going to use Make. That being said, there are a lot of people that use CMake. CMake is a cross-platform version of Make. It also has a couple of other benefits. And typically the people that use CMake swear by it, and the people that don't swear at it, but that's just how CMake works. There's also a lot of other types of Make files that are out there. So SOCONs, or SCONs, is it's a system that tries to automatically generate your Make files that I know some people at Penn State use. There are some others. So WMake is a specific version of Make that's built for OpenFOAM. QMake is for Qt. A lot of these are very program specific. And so it's one of those things where you might not necessarily want to use those things, but depending on how your program is set up, you might be forced into it. And hopefully the documentation is there. You'll be able to wade through it. But for the most part, these are typically built as extensions of Make, and so that's why I think that Make is a good place to get started. Make uses what's called a Make file, and the Make file has 3 separate sections. So one of the sections talks about the outputs. Right? So it's really just listing out, these are the things that are going to be created. And those can be either executables or libraries. The second section is where you list all of the dependencies. So the dependencies are saying, all right, so for these things that we're trying to create, this is what those things rely on. Then the last section is the instructions. So how to either make or find each of those dependencies. So the Make file is a little bit complicated, but just remember those 3 things, right? So outputs, dependencies, and instructions. The other difficult thing with Make files is that, some people really know what they're doing, and it's hard for a beginner to look in those things. We'll talk a little bit about both how you can set environment variables within the Make file, and so then that way, if there are things that are repeated often, you don't necessarily have to repeat them every time. And then also, the other thing, there's some shortcuts for sections that are often repeated. So some of these are very easy to understand. However, some of them, because of the regular expressions that are there, are very difficult to understand. So we'll kind of introduce that a little bit in our example. We'll take a look in at what I'm calling an advanced, or a more advanced Make file. And so just so that you're aware of what might be out there. It does get pretty confusing pretty fast. So let's just go through a basic makefile really quickly. We'll look at this again in our example. We'll compare it to a little bit more advanced makefile at that point. But here, so again, we have this factorial. So this is this is the executable that we're going to create. And just so you know, this is actually the example that we're going to be working through here in a few minutes. So in that code, we have we're creating an executable called factorial. And in order to create factorial, we depend on these different objects: factorial.o, readinvar.o, and factcalc.o. So within factorial, all it does is it calls a subroutine called readinvar, which is in a separate file, and that says, all right, what number should I take the factorial of? And asks you to input a number. And then factorial calls factcalc, which actually calculates the factorial, and then it spits it out to you. So that's why I apologize, this is way more complicated than a factorial example needs to be, but I'm hoping that by using something so simple, we can very clearly understand what's going on, both with the make as well as with the debugging that we'll be doing here in a little bit. So our factorial is going to rely on all those things, and then we build it in this way. And so then one of our dependencies is factorial.o. So we're saying that factorial.o relies on this, and we build it in this way. One of our other dependencies is readin.o. It relies on this, and we build it in this way. Right, so that's kind of how we look at this makefile. We have the overall executable on the outside, we have the dependencies, and then we have how to make all those dependencies. So again, we're going to look at this with a few more advanced features in our example here in probably about 10 or 15 minutes. So I have some tips and tricks, little hints for how to use make. One of the most infuriating things about make is that it requires you to use a tab or second lines. If something needs to be over-indented a little bit, you must use the tab. When you're running make, there's a couple of flags that I think everybody should be aware of. The first is the -J flag, and then you give it a number of processors that you want to do the compilation on. Typically, makefiles are called makefile. But you can call your makefile anything you want, and then use whatever makefile name you want with the -F flag to change which name you're using. So those are some things within make to be aware of. A couple of other things that I just think are helpful to know. So the env command prints out everything that's in your current environment. So if you compile the code, everything is working right, you might write out or use env to put everything that's in your current environment into a file. So then that way, if something isn't working later, you can compare your existing environment to the environment that you know everything is working correctly in. LDB is a command that can be used. So if you run an executable or are looking at a library and you don't know how it's compiled, you can use the LDB command with that either executable or library, and it will tell you all the different things that are being used. There are, so make is a great thing on its own, but there are some ways to get some of the features of your local cluster and put those into the make file. And typically that's done with the configure step. So if you see a makefile.skel for skeleton, or makefile.input, or makefile.in, a lot of times that's and those would not run if you use make. A lot of times that indicates that you're going to need to put in a configure step. And especially when you're putting in a configure step, you can change where that build is done. So that way the source code and the build are in two separate locations, just so that you know you don't accidentally mess something up with the source code that's there. Make has some great resources. The man page is actually pretty good as far as complicated man pages go. And then GNU has a huge manual online with a whole bunch of different example cases. All right, so now the bulk of what we're going to be talking about today is within this, what I'm calling code optimization stage. When we're getting our code running and running well, those are kind of two separate steps that are very much linked together. So we're going to look at a lot of different ways that will help us as the user identify what parts of the code need some help. So the first thing that we always want to look at is are we getting the right answer? You know, is the code doing what it's supposed to do? And then the second thing is this code running as fast as it can, right? So I want to both do my analyses as quickly as possible so that I can do both more analyses as well as write my papers and be done and move on. And then with that, the other thing is, you know, especially on, say, ACI, if you are sharing an allocation with many other people, you want to make sure that everybody's able to do as many computations as they can. So with that, you want to try to optimize your code to take up as little of the CPU time as possible. And so again, I keep coming back to this every time I do the seminar. I'm highly suggesting that you find a representative problem, your small test case that you know the answer to, and that it's small enough to test and run quickly so that we can try out a bunch of different things on it. Okay, so a lot of people talk about debugging and profiling. In theory, debugging is trying to figure out how to make sure things are running correctly, right? So you set breakpoints, you can look at variables, you're trying to figure out, am I getting the right answer? And if not, why am I not getting the right answer? And then profiling, you look at, as my code runs, here's what takes long periods of time. So these are the types of things that I should be working on to see if I can figure out how to make them run better. Now, so that's kind of how things are in theory. In practice, these things are very much linked, right? As soon as you try to change something so that your profile looks nicer, so that things run faster, you're always going to introduce bugs. So you're going to be going back and forth all the time. And so rather than talk about, you know, debugging as a step and profiling as a step, I've developed for myself a little workflow that allows me to do make my improvements as quickly as possible. Right, so it's not necessarily tool or method agnostic, but it's this idea of here are things that are easy to do, these things are more complicated. So I'm going to hit all the easy things first to figure out if that's going to do what I need it to do. And if not, then I'm just going to get, I'm going to use analyses that are more and more complicated. So typically what I try to do is the first thing I do is I look at past processes, things that have already run. Right, so I want to, before I do anything new, I like to look, you know, both at the log files and then maybe at the trace job output if I ran this on a batch system. The next thing that I'm going to do is I'm going to look at processes that are running right now. Right, so if I've started a bunch of jobs and I realize, oh, this is going kind of slow, let's take a look. You can use either top or PS on processes that are running on, if you're on the machine that it's actually running on. You can also use show Q minus R to get a little bit of an idea of what the efficiency of that running process is. If you're going to restart something that, or start something fresh, one of the things that you can do is add this USR bin time and then minus V for verbose. That gives you quite a bit of useful information as far as, you know, how much CPU time is actually spent churning on things and how much was spent by the system waiting for other things such as I/O. So one of the first things that people do is put in print statements so that as their code is running, you're printing out variables that, you know, every time something gets incremented or every time something happens. That's pretty useful for debugging. And then if things are going really wrong, you can run strace on your executable, and that gives you a boatload of information, but at the same time, it can be very, very useful. The most difficult thing to do is to do some sort of instrumented run with either a debugger or a profiler. And so I'm not suggesting that you not use those tools, but I would highly suggest that you try some of the easier things before you get down to this stage. Because if you're going to put all that time and effort into getting things running in the profiler, only to realize that there's some simple things you could have fixed that you could have looked in your log file for, you know, it's just a waste of your time. All right, so this first step, look at past processes. Right, so a lot of codes that run will produce some sort of output file that has some statistics about the run in addition to whatever output you're getting from the actual analysis. So specifically, I like to look at memory usage and CPU time, and then also the number of threads and the number of cores that are being used, trying to make sure that I'm putting something onto the system that's going to be running well. For batch jobs, you can get a lot of this information using the trace job command, although I think that right now in ACI, users cannot use trace job, right? We have to log on. So we switched around the way that things work, but we can get you that on your jobs. If you email the IS Center, they can give you the portion of the trace job output that would be relevant for you. All right, so the next step is to watch processes that are running at that time. So again, the memory is going to be one of the most important things. The CPU, how much CPU is actually being used is very important. There's also something that's called the status of the job, and we'll talk a little bit more about that here in a few minutes. I highly suggest using top. So top is a command that tells you everything that's going on that computer at any given time. So top with the capital U, and then your username will limit it to just your processes, which is very, very helpful, especially if you're on ACI, which we will be later on. So top is running these things in real time. You can also use the process snapshot command, PS, and then I typically use the AUX flags and grep for your username to get a lot of that same information that's found within top. And then for batch jobs, so if you use show Q minus R, one of the columns that's shown is the efficiency of the job. That's off by roughly a factor of 2. Your efficiency is supposed to be between 0 and 100%, showing between 0 and 200%. I don't know exactly why that is, but the higher the efficiency is, the better you are. That does not work well. If anybody here is on CyberLamp, uses GPUs, that does not work well for the GPUs. The efficiency only looks at the CPUs. And then one of the other things that you can do is log on to your job's nodes. So the nodes that your jobs are actually using, you can find with this qstat command. So -n1tu, and then your username. Don't use my username. That's not going to get you too much. And then once you know the node that your job is actually running on, you can SSH directly onto that node. And because you're running a job on that node, we'll put you on the same processors that your job is running, and then you can use either top or PS. That will affect, in a minor bit, how well your job actually runs, especially if your code is very well compiled, because you're going to be using the same processors that are assigned to your job. But for the most part, that's not going to make all that much of a difference. Top is very powerful. There's a help within top. So once you start top, you can type H. It will bring up a bunch of different things, show you what to do. When you first start top, everything is sorted by the amount of CPU. Right? So the hardest CPU burning processes are the top, are listed at the top. And then the second thing that you can do, if you type capital M, you can sort everything by the memory usage, which can be very helpful, especially if you think that your problem might be memory bound. You're also able to kill processes. So within top, the leftmost column is the PID. And so if you type K and then the PID, I apologize for I did this on one computer, and then I guess I don't have this font installed on this computer. But K and then the PID, it'll kill that process. You're not able to kill anybody else's process, but you can kill your own. And then there's also a status column. The status that you most often want to see is this R for running, but then S for interruptible sleep. That's also something that's pretty common. That's typically that you're waiting for the next event to occur. That happens a lot with I/O, as well as if you're calling other functions that actually start new processes. Outside of that, if you see Ds, Ts, and Zs, you're probably in trouble. Those are uninterruptible sleep, so they're things that are just dead. Zombie just means that the system has tried to kill that process, but it lives on. And then if you're using PS, it'll tell you what's actually running in the foreground, as well as if one of those things are the session leader, if you're spawning multiple processes. We are going to be looking at our example using top when we're running this here in just a few minutes. Okay, so if you're going to be starting new jobs and trying to figure out what all is going on, you can put some simple extensions within there to help get a few more statistics to help you understand fully what's going on. So I mentioned before this USR bin time, and then the -b for verbose, and then you put the exact command that you were going to run before after that. So I can do manless transactions and only print it out if it's a charge. So this can be very helpful if you're looking for your job IDs. For example, if you want the IS Center to give you some trace job files, you probably want to give them what job IDs you have. So you can look at all of the different things that you've done that have been charged using this manless transactions. But again, the important part here is the USR bin time. And again, the most simple thing for debugging is almost always going to be to litter your source code with print statements and print out anything and everything, so that way you can track to see what's actually going on. It's far easier than full debugging, trying to get a debugger up and running, especially for complicated code. But you're only going to get the information that you ask for when you ask for it. Debuggers will give you far more than that. And then with that, there are some difficulties when you start to use either parallel code, because you might be getting answers from a lot of different processors. You have to print out which processor I'm on, as well as the information that you want to use. And then if you are having some systems issues, so strace or the catch segv, these are two things that are useful. They give you an overabundance of information, but that being said, if you're having problems where something's actually, you have no idea what's going on, that might at least give you a few things to start looking at, start poking around at. The last step, the most complicated thing to do when you're trying to get your code running and running well, is to use either a debugger or a profiler. And I kind of talk about this idea of there being a spectrum, right? So it's not, there are very few tools that are just debuggers and only do that, nothing else. There are very few tools that are just profilers, only do that, nothing else. On the more traditional debugging side, GDB and DDT are two of the most commonly used. We'll be using GDB here in just a couple of minutes. Someplace in the middle, Total View and Valgrind are both there. Both of those allow you to get some of the debugging things, some of the profiling things. And then Tau and Btune are probably the most commonly used things for being profilers. However, both of those are far more powerful than just profilers. You can do a lot of debugging within those if you know what you're doing. One of the things that I do want to point out, so I think all of these except for Total View are available right now on ACI. Vtune, one of the nice things about Vtune is that Intel has a couple of, I think 7 or 8 different tutorials that are online. And those tutorial files are actually found within the module on ACI. And so you can just copy those. If you're looking at the tutorial link here, it'll tell you where to find those files. So you can just copy those directly down and use those tutorial files. It's actually they're very well done. I've been appreciative of that on several occasions. So my biggest suggestion, because all of these are large, powerful tools, is to see if you can find a tutorial that does what you're trying to do, right? So if you're looking at cache hits, try to find a tutorial online, figure out how other people look for cache hits. And that'll probably tell you, all right, which type of tool do I want to use? And here's a basic workflow for extracting that information using that tool. Almost all these tools, the debuggers are a little bit more on the debugging side, but can do some profiling. The profilers are a little bit more on the profiling side, but can do some debugging. If you do want to learn a single tool very well, you might be able to do almost everything within that tool. But because other tools are typically better for other things, it might be hard to find the documentation or example in order to do this. So again, one of the things that we talk about a lot within ICS is there really is no silver bullet. None of these are a perfect thing for everybody. It's going to work for everybody well right out the gate, but almost all these tools have advantages that are going to make looking for something very, very easy. All right, so we're going to be using GDB here in our example, I think on the next slide or maybe one after that. But one of the things when we're going to be doing with our example is that we need to compile with the -G flag. That makes our executable much, much larger, but even if you run with that, it's not going to make that much of a difference, if any difference, if you're just running the code separately. And then we're going to run GDB with our executable. Within GDB, there are a couple of commands that we should know. So run just runs directly through the problem. We can also set breakpoints using the break command. So breakpoints are places where we'll run until that point in the code is reached, and then we're going to stop. And when we stop, that allows us to interrogate the different variables using print statements. So we can print out what all those individual statements are. And just to be clear, we can set breakpoints either within files, and that's part of the reason why I made our simple factorial example use multiple files, or within functions. The other commands that are commonly used that we'll be using in our example are the step function which goes to the very next thing, as well as the continue function, which goes until the next breakpoint. So you can step through your code line by line, or you can continue until the next breakpoint. And I do want to be clear, there's something, so the step function steps through the assembly code, right? It doesn't step through your code how you have written it out. So if you've used a lot of different optimizations or loop unrolling, things like that, sometimes the step function moves you to places that you don't necessarily think you should be moving to if you're looking just at the source code. But that being said, when you do the step function, it'll tell you exactly where in the source code you are. And so even though it might be confusing, you'll at least know exactly where you are, even if you don't know exactly why you're there. So just a few quick notes before we jump into things. With debuggers and profilers, because they're using the assembly code and not your code, it's often difficult to follow if you're looking at ordering of things within the code, if you're doing a lot of optimizations or different things like that. But for the most part, they almost all give you line numbers or what the lines are or the file that you're in, so that it's easy enough for you to track that, regardless of if it's running in a way that lines up with the code or not. And again, use trial and error, especially if the real things that you're working on are very, very large. It's almost always going to be easier to deal with a smaller representative problem, even if you're just doing that to figure out the process you have to go through when you switch over to a larger problem. Some things to do once you've figured out what's actually wrong with your code to speed things up is to either modify your code or add some different flags to try to take advantage of the cache size on your cluster, some loop unrolling that you could do. Some of these, so for example, we've been talking a little bit about SIMD, so single instruction, multiple data, in the CSE 597 class that Chuck, Chris, and I are teaching. But all of these are things that you could potentially do in order to speed things up without making any other real changes. The next thing, in my experience working at ICS and my experience in my own code, one of the things that takes the longest, the biggest bottleneck is I/O. And so if you can write out your I/O in parallel, that's almost always going to speed things up for you. I would say probably 70% of the speed up that I've been able to get in my own personal code was because of the parallel I/O issue. The next thing is with algorithms. So if you're doing something like a matrix multiply or a matrix inversion, you can write your own versions of those, but chances are somebody's written a much better version of that. So take advantage of these libraries that other people have written. And these are for serial as well as parallel things. There's a lot of great things that are out there that you can find online. We also have a lot of these built in as modules on our system that you can take advantage of. And then one of the other things to think about, especially for parallel jobs, is communication while the job is actually running. So we're going to both try to reduce the amount that gets communicated between processors as well as the frequency in which those things are communicated. So these are kind of the biggest things that you're going to be looking for. And again, these things are going to be very specific to your own project, maybe even for different runs if you have different sizes of things. There might be different things that you could do with the algorithm. So you could almost always say that anybody that's doing this for their own code could probably get up here and give an hour-and-a-half lecture on exactly what they're doing. And most of the other people in here might find a few things that are interesting, but overall it's not going to be all that useful, just because all of these things are so problem-specific. All right, so now let's start working on our example. We've already seen the makefile, for example. We're calculating factorial. We have the functions both to read in the number that we're going to calculate with, as well as to calculate those. Those are in two separate files. And so we're going to use Git to actually get these files on the cluster. We're going to work a little bit with branches. We're also going to use make. We're going to look at a couple of different make files. We're going to use GDB to find a bug in this code, and then I'm also going to have just a couple of other random little tricks throughout this. So if you guys want to pull up Exceed on Demand, we're going to be kind of doing things in incremental steps. So the first thing that we're going to do is we're going to open up a couple of terminal sessions. Application System Tools Terminal, and then so open up a second terminal and put it kind of down here at the bottom. And what we're going to do in that second terminal is start top. So if you remember, we do top and then capital U and your username. So right now I'm just running top. You see everybody that's on this particular node. So the columns that are most interesting to us, so we have the PID, we have the user, eventually that's going to be just me. We have the command that's running, the amount of time that's running. We have the CPU, so that's per processor. The percent mem is actually a percentage of the entire memory on that system. So rather than looking at the percent, I typically look at the virtual, the resident memory, so that's the memory that has to stay in RAM, and also the shared. But so that the vert and the res, those are the two columns that are most interesting here. Okay, so now, if you look, I'm the only user that's being represented here. So these are all my particular tasks. So hopefully you guys can put in your username, you can see exactly what you're doing. We're going to come back to this and look at this at a couple of different points throughout the rest of what we're doing. So that way you can hopefully see how this might be useful when you're working on your own processes. All right, the next thing to do is we're actually going to get online to your Applications, Internet, Firefox web browser. And we're going to go to, close this one. We'll go to github.com. I'm going to search GitHub for ICS Seminar 4. So you'll see that I've made a Git repository. Adam Lavely, that's me. That's my GitHub name. I don't use GitHub very often. I think that this is actually the only publicly available repository I have on GitHub. So if you click on that, you can actually see all the code that we're going to be using for our example today. And the important thing here, it's this clone or download button. Right, so if you click on clone or download, it gives you this web address. And so we're going to be using that now to bring those files back to our local computer. So in our main terminal, go to some place that you want to be working at today. So I'll go to my work directory and I'll make a directory called 16feb. And then you'll do git clone and then this address here. And so that's going to clone everything that's up on the GitHub repository into our own computer. Okay, so the next thing you need to do is just change directory into that directory. So this is where the repository lies. And do an ls-a for all. One of the things you'll see here is this .git directory. And this is where all the magic happens, so to speak. That's where all the different repository files are kept and stored. If you look in there, those files are incredibly difficult to understand. I highly recommend that you just leave that alone and don't ever touch it. We can do everything that we want to do using the git commands and not messing with the files in that directory. Previously, we looked at a makefile, and so I think that is makefile basic. We just want to bring that up. I have a little header that wasn't included on the slide, and I also, the only other difference here is that I have this clean section. The clean section allows us to get rid of all the object files, as well as any other files, such as that executable. So that way, if we want to make sure that we're getting a fresh start, we can run clean. And then when we run make again, we know that it's going to make every single thing that's in there. So again, we have the executable, we have all the dependencies, and then we have how those dependencies are actually created. And you see here that all of these are tabs, and I realize now in my slide that that tab didn't actually come out. So this amount of space here has to be a tab. That cannot be spaces. There's also a makefile. So if you want to open that, that's with a few more complicated things, but again, still fairly simple. So if you remember from our previous thing, we had a compiler, this GCC, that was used all the time. So I'm going to set this as an environment variable, and I'm going to use that all the time. So what that means is that if I want to change compilers, as opposed to changing it every single time here, I just have to change it once. And then also, the flags that I used, so I think that in the original makefile I only have the -c, but in this makefile I have a -g as well. So this is pretty standard for a make file. We want to make it as easy as possible to switch the compiler. We want to make it as easy as possible for us to switch those flags. And so because those things are repeated all the time, we're going to set those up once and just be done with them. Now, if you want to take a look, there's also what's called Makefile Advanced. And this is where it starts to get a little bit more complicated. So instead of listing out how to make all those different sources, we're going to just list out what the sources are. And then we're going to list out for each of those sources what the object file is. And then for each of those objects, we're going to create it with all these things. Right, so again, this is just a way of saying, all right, we're doing the same thing over and over and over. How can we do that once and not again? Right, so we're doing the exact same thing here. Factorial.o depends on factorial.c. And we do this on factorial c. Readinbar.o, readinbar.c. We do this on readinbar.c. Right? So rather than repeat those things, we're just going to set those up once here with our sources and objects, and then for all of our executables and all of our objects, we do the exact same thing. You've gotten a repository from somewhere else. That's currently the master branch. So now the next thing that we want to do is we want to work on this a little bit. So let's create our own branch for this. So our command is going to be git checkout, then -b for a new branch, and call it something that's meaningful to you. So I'm going to do AWL 5173 debug. If you do git branch, it'll tell you what all the branches are, so that way I don't have to remember this, and I know exactly what branches there are, so that way if we're going to merge later or something else, it'll be helpful for us to know exactly what's available for us. Now, let's run make again. So with this, we'll run factorial. It asks us, all right, what do we want to calculate the factorial of? I'll say 5, and I know that this is not the right answer. So we're going to use our debugger here in just a minute to actually figure out why we're getting the wrong answer. All right, so our next step is going to be to actually run the debugger itself. We use GDB and then the name of the executable. So we can run the executable from within GDB. So if I just type run, it's going to run almost as if I was on the command line without this, and give me back the same answer. It's going to give me a few other things, but we can use it in much the same way. So, as opposed to just running it, let's set some breakpoints, and we'll start to look at what some of these variables are. So if you remember, the way to set breakpoints is by using the break command. So we can set up a breakpoint in a function, so main, 5, so the 5th line in main function. And then we can also set up in a file name. So in calc, let's go 10. So now we've set up a couple of breakpoints, so when we start to run, when we hit these points, it's going to stop. Right? So previously it only stopped because we had to enter something in, and then it just ran just as usual. So if you type break, and then either a function name, and then a colon for a line number within that function, or a file name and a line within that file, it'll set a breakpoint at either of those locations. So when we run, it's going to stop us as soon as we get to the first breakpoint. So one thing to note is that when you set a breakpoint at, say, line 5, if there's nothing there, if line 5 happens to be white space, it's going to wait until the next location where something actually happens. So even though I said 5, it's actually stopping at line 20 because I have a whole bunch of comments at the top of my code. So it stopped here. We have full access to everything that's within memory. So what I'm going to do is I'm going to say, all right, print input. Right now input is 0, which is a good thing. We haven't actually given it any input. But we can print out any of those variables that's there. Okay, so we can then continue, which will continue out to the next breakpoint, or we can step through. Let's step through a few things just so you can see exactly what's going on. So the next step, this is the line number, so that way if you're actually trying to debug this, you can very easily figure out where you're going. calculate the factorial of something. We'll step again. This is where it's going to ask us what we entered, or what we want to calculate. Git step again, now we're actually going to be prompted for that. Okay, so we entered 5. Let's make sure that we're actually getting what we were supposed to do. So we can print input, and hopefully we get 5, and not the 0 that we had again, or had earlier when we asked to do this the first time.
You said the step is how many lines?
No, so the step goes to the next thing that the assembly language is trying to do. So it's not a number of lines, it's to the next thing that's being executed. So yeah, so step is to the next thing that's being executed, continue is to the next breakpoint that you have. So we'll take a few more steps, and here's where things actually start to get interesting. So within FactCalc, excuse me, what we're doing is we're going to, for each of the counters that we have, up until the input variable that we give it, we're going to multiply, maybe we'll just, we're going to multiply the output val by counter, and that's how we calculate the factorial. So if we do some print statements here, we print the counter, we can print the input val, oops, print input val, and print output. And you can see that here our output number is incorrect. And so what's actually happening in this very simple example is that we don't initialize what that output value is, and so it takes whatever's in memory at that time. So even though we're multiplying by 1, 2, 3, 4, 5, it's not getting the right answer. So, long story short, we're going to now make that change. In order to do this, I'm going to open up that FactCalc. We see here that output is not initialized. So we're going to say output equal 1. And then I'm also going to change this so that we go less than or equal to input value. I just made 2 modifications. I put output equal to 1, and then I said counter less than or equal to input value. So now if I do make, the only file that was updated was this FactCalc, and so I'm creating the object file for that, and then I create the factorial output using that new object file. So it didn't go through and remake everything. It only goes through and remakes the things, only goes through and remakes the things that you've updated.
Why don't you do make clear in this case? Because you wish.
So the other object files are still fine.
Okay.
I have no reason not to use those. I've only changed the one file, so I don't need to blow those away. I can keep those and just update the one with the file that I've modified.
Okay.
So to repeat, we've only modified one file. So now let's do a little bit of Git magic to put that back in. So we can do git add factcalc.c. That's the only file that we added. Right, so now I've staged this. So now I'm going to commit this in. So git commit. Okay, so it's telling me that the only file that's modified is factcalc. Git also tells me these files are in here, are in this directory, where we have our Git repository, but you're not tracking any of those. And if you see, they're the object files and our executable file. Because all that I really care about is the source code. I'm not going to track those files. So I'm leaving those untracked. But it is nice. Git tells you when you're doing the commit exactly what's being modified and what's going on. So Git gives you the opportunity to label each commit. So I'm going to say, update factcalc due to bug issue. And then we're good to go. So I've labeled it. It says that one of my files has changed. I have 2 insertions, 2 deletions. That's just what's going on within the file itself. But our git commit is now complete. Okay, so we've updated that particular branch. So if you remember, so we're in the AWL 5173_debug, whatever branch you're using. So now what we can do is view the exact changes that have occurred. So I can do git diff and master. So if you remember, the master is what we had originally downloaded. So from the master, I deleted an empty line, and I added a line that said output 1. So I can use diff to be able to look at the differences between different branches that have already been committed. Okay, so the other thing, I'm not going to do this now, but you could eventually push this back up to either GitHub or some other location. And then the other thing that you can do is merge the new branch that we have back in the master if we say, yes, this is exactly what we'd like to do. The one other thing that I'd like to point out is that Git has this log. So if you do git log, you can see exactly all of the different things within that branch that have been done. So here, when I first started, I created this. My initial commit was creating everything. I realized that I didn't have a README file, so I had another commit that put in that README file. And then I actually had commented the code for myself just so that I could keep things straight. So I had another commit where I updated things and I deleted unneeded comments. And then now we've just done this where we updated fact calc. If you remember, this is what I typed in when I was labeling the commit. So it's possible to go back to something else. Say, oh, you know what? I put this up. I realized that I should not have done this. And so what I can do, so each of these commits has this huge long number. I can go back to any of those. So if I can go back to that as a branch. So if I do git checkout, and then I'm going to create a new branch, and I'm going to say run back to this. So here I'm going back to this VA. I don't have to include that whole thing. I can just include enough of it so that it's unique. And for the most part, you only need 5 or 6 characters. But this does allow you to create a new branch, to go back to something else. That means that none of your code is lost. You can always go back to what you've done, or go back to what you had originally done. It's just going to be a little bit harder to track within those Git logs. Okay, so that's an example that uses Git, some of our version control, make some of our build automation, and then GDB, a simple debugger. All of these are just scratching the surface. Again, as you do your own research, you're probably going to be doing things that you use maybe this, maybe something else, but hopefully now you know enough of the terminology to be able to poke around on Google and figure out what you need to do. The last thing that I want to talk about is scaling. So I didn't talk about scaling and code optimization, but the reality is I probably could have. Right, so scaling is code performance testing. Right, so you're trying to identify for your code how well it performs either on different problem sizes or on different computational resources. Okay, so I suggest that people do scaling to help diagnose these profiling type issues before they even try to run a profiler. That doesn't necessarily work for serial tasking all that well, and also has some different issues, especially if you're using threads. But it's a good place to get started. One of the other things that I often use scaling for is to find, for parallel jobs, the range of number of processors that I should run this job on for it to run reasonably well. And I'll show you what I mean here in just a little bit, in just a couple of minutes. The other thing that's nice with scaling is that because you know exactly how much time it takes to run something, run your sample code, run a couple of pieces of code, when you're trying to figure out, all right, so how long is this next analysis going to take, you can use that to inform that decision. And then the real reason why most people do scaling, or at least why most people get started doing scaling, is that they're writing a proposal to either the NSF or to DOE or somebody else asking for computational time. So for that, they're looking for those scaling studies because they want to know that your code is ready to run on that cluster, and that the time that you're asking for, I'm requesting this many computational hours, is accurate. You can say that it's accurate because you know exactly how long things are going to take, you know how many runs you're going to do. So that's why most people get started with scaling. Now, if you want to learn more about that, or learn more about applying for computational time, especially on the NSF clusters, talk with Chuck back in the back. You see at P102 at psu.edu. He can help you get a starter allocation on those exceed resources so that you can do these scaling studies in order to write your proposal. Talking to Chuck is by far the best way to get started for that. So I've done NSF Exceed I did that for most of my PhD. I also ran a little bit on the DOE. I put in DOE inside proposals. I never won one of those, so I can't tell you anything about what a good insight proposal looks like, but we can help you get up and going with anything else. But there's two types of scaling. So strong scaling is finding the efficiency for a fixed problem. So if I have a problem this size, I'm going to run it on one processor, I'm going to run it on 2, on 4, on 8, on 16, on however many processors to figure out how quickly my code, or how efficient my code is when I scale more processors. So we're going to choose both the number of processors that you run on, as well as the starting point for your normalization, with a little bit of intention, with a little bit of purpose there. Especially on the NSF clusters, you're going to be wanting to try to use full nodes as opposed to just on a single processor. If you do look at single processor, comparing there, oftentimes you're going to get a linear speed up because of either availability of RAM or potentially even cache hits. So this is strong scaling for code called VASP on ACI 1.0. The simulations were done by Chris Blanton and then I plotted these. So a code that scales perfectly well says that if I double my number of processors, the amount of computational time that it takes is going to be cut in half. And if I multiply my number of processors by 4, my computational time should be cut in half. So we can measure this as what's called a speed up. So a perfect code is this dotted line, and then what's actually happening is blue. So we do get a little bit of superlinear speed up here, but that's because our problem size that we chose for this was too large to fit in all the RAM for a single processor, and so when we jump up to multiple processors, based on our RAM limitation, we actually don't have to go out to disk, and so it runs a little bit faster. So this is kind of saying that we're running pretty well. Okay, so this is for VASP. When I was doing simulations, so I wrote an NSF-ACI proposal for Stampede a couple of years ago that got partially funded. This is what I used for most of my PhD work. So I was looking at an actuator line of a wind turbine within an atmospheric boundary layer. And so rather than start it on one processor because my problem was far too large for that, I started on 64, which I think at the time on Stampede 1.0 was 2 processors. So I do a scaling here, and I show that I'm scaling reasonably well compared to ideal. This is the traditional way that scaling is shown, but one of the other things that people do is plot it in terms of efficiency. So instead of plotting next to the line, you're plotting how far off the line you are. So you're dividing your value by the value of what that perfect scaling actually is. So here, you can see that at low numbers of processors, I do have slight superlinear, but even at 512 processors, I'm still running at roughly 92%, 93% efficiency. And so in my NSF-ACI proposal, I said I plan on running. I actually did this. I said I plan on running on 256 processors because I'm still running at about 98% of peak efficiency for this problem. And they said, hey, 90% is pretty good. Maybe we should give them some computational time. And now I have a PhD.
Excuse me, for the second point from the left, why the efficiency is beyond 100%?
Yeah, because the problem size was too large for 64 processors. I needed more RAM than those 64 processors had access to. And so because of that, it had to go out to disk for some of the memory. So when I switched to 128 processors, I had more memory available to me, so it was all able to stay on the RAM itself. So yeah, the superlinear speed up occurs primarily because of RAM issues, because you're using too few processors, or normalizing for too few processors for your problem type. Right, so the other type of scaling, and this is my last little section here, or last little real section, is called weak scaling. And so this is for a given amount of work that each CPU does, how does it do as we make our problem larger and larger? So if I have a problem of this size on one processor, I'm going to have a problem of this size on 2 processors, and this size on 4 processors, right? So each processor is getting the same amount of work, we're just making our problem larger and larger. A lot of people will use weak scaling to compare different codes and understand, all right, if I'm trying to do this analysis, which code should I be using? And then a lot of other people, they're trying to figure out what's the biggest problem I can do. The astronomy people, how many different galaxies can I take into account? How large of a problem can I get? It's much less common than strong scaling, but it's a very useful thing to work through. So this is a weak scaling plot for, it's a boundary layer code that I wrote for Phil Morris's Aerospace 524 class in 2012 or so. So you'll see with one processor, I'm at 1, that's my normalization point. As soon as I have to do all the MPI communication, I drop off fairly drastically. And so that's kind of these in here. And then as soon as I jump onto multiple nodes and I have intranodal communication, that's a whole other layer of complication. So that's this drop off here. So for this particular code, I didn't actually do this for the class, I modified it later on, but I would typically run on 16 processors because I was still running well above 90% efficiency, and so that was good enough for the purposes that I was doing there. So we do have some documentation online that's growing all the time. There's also fantastic documentation done by Exceed, the NSF-Exceed program, that's available here for any of the, you can do this at any time. And then Chuck runs the Exceed classes. They also do live classes that are like 1 or 2 day events on different topics. So yeah, the NSF-Exceed is great online training that you can do at any time, as well as classroom type training that ICS puts on. The NCSA at the University of Illinois has a CI tutor program. There's a lot of great resources within there. Hopefully I've given you enough terminology that you at least know how to get started in your own Googling. Something else that I also suggest people do is look at places that have batch clusters similar to what ICS has with ACI. Look at TAC, look at the Ohio Supercomputing Center. Brown actually has some excellent documentation for their profilers for both VTune and Tau. So these are great places to get started, and hopefully you can find something similar to what you're doing so that you have to modify as little as possible. And with that, thank you for your time. Happy to take some questions now. Feel free to stick around afterwards for, if you have some more detailed questions that aren't necessarily relevant for the whole class. But thanks for coming out.
Why did you choose, it seems like if you could use more resources, the efficiency is not as good, but you could do it faster. What is a good goal to set, where, let's say if you were sending a proposal?
That's an excellent question. So here, I was really trying to say, I want to be as efficient as possible, and if I run on 256 processors, I'm going to be 98.8%, 99.1%, something like that. Very efficient, right? So I'm trying to convince them, you should give me as much computational time as possible. You do get quicker answers if you run out here. You just are running less efficiently. So, I mean, my rule of thumb is probably, if you can show that you're above 90%, you're probably good to go.
90 is a good.
Yeah, I think 90 is probably a pretty good number. But that being said, if you can show, with minor modification, I could potentially do a little bit more. But yeah, the most important part is that you're using this to give them accurate numbers. This is how much CPU I need. This is what my reward needs to be. And then how you actually do it once you get that award is kind of up to you. So, yeah, nobody's stringent enough that they say, all right, you wrote a proposal for this, you must run this. So you can get the proposal for this amount, say, you know what, really, I only need this many runs. I'll run it at a slightly lower efficiency, but that I can get the answer quicker. Nobody's going to bat an eye. Yeah?
Efficiency, how do you measure it? It's just the time or
Yeah, so
speed?
So really what we're measuring is the ratio between here and here. Right, so this is, I don't know, 90-ish% of that, right? This is 80-ish% of this. And yeah. So this efficiency ratio is saying, all right, if I run it on a set point, either one processor or here, in this case it was 64 processors, how much faster per CPU am I going to be getting my answer? And so there's a little superlinear here. Here it's a little bit slower. You're getting your answer in wall clock time faster, but not in CPU time faster. Right, so that's the real difference, is that you have the total amount of CPU time that it takes versus the wall time. So I was talking here, these run much quicker, right? I'm running on far more processors, so I get the answer faster, but that doesn't mean that it's more efficient in terms of the CPU time that's required.
So in that case, say you are competing with somebody that runs same site but better efficiency, he probably gets the NSF.
So with the NSF, if you're going to get an award, chances are you're not going to get your entire award. And so you're not necessarily competing for the award, but you're competing for how many hours they're going to give you. So, but yeah, they're going to be comparing all those different things. They're also going to be comparing your science. So it's a game. I don't know the best way to play it. Yeah, Chuck, do you have...
If you're going to go for an Exceed award, which is generally another NSF style one, they have documentation and tutorials online that show you how to go about writing a likely to be funded Exceed proposal. And the idea is that they suggest that you take the starter allocation, prove that you know what you're doing, because that's the first thing they want to make sure is that you're not going to waste it. And then that scaling things that Adam is suggesting are huge for success. So, as he's alluded to, you might not get the whole thing, but if you can prove enough scaling on a decent enough, interesting problem, the typical success rate is around 75 to 80%, so it's really high.
If you follow that.
If you follow the formula. If you don't follow the formula, you aren't going to get a proposal funded.
Okay. Well, feel free to take off. It is Friday afternoon. If you have some other questions, you can ask me, ask any other guys around. But yeah, good luck with your computations.